Hello and good day. Welcome to CHEL 101. I am Dane from Chen Academics and I will be discussing optimization problems under Calling 1 Differential Calculus. So here is an outline of the topics that we will be discussing today. First, we will tackle the formulas needed as well as the steps in solving optimization problems, an illustrative example, and finally, to wrap everything up, a quick summary. As for the formulas needed, it is a must that we know by heart all the formulas for area, surface area, volume, perimeter of different geometric figures such as quadrilaterals, triangles, circles, spheres, and so forth. So let's start with the basics first. For the quadrilaterals, we have the square, rectangle, parallelogram, trapezoid, rhombus, and kite. And we might be familiar with most of them from high school days. The area of a square is x squared or s squared, as for side. Rectangle is length times base or sometimes length times width. Parallelogram is base times height. Trapezoid is 1/2 of a plus b times the height. Rhombus 1/2 times d1 times d2, and kite is 1/2 times d1 times d2 as well. And as for the area of a triangle, we have 1/2 times base times height. And for the perimeter, just remember that it is the sum of the length or the measurements of each side that encloses the polygon. So in this case, a plus b plus c is the perimeter of a triangle. Next, we have three-dimensional shapes as well, such as cylinders and cones. So the volume of a cylinder is pi r squared height. And simply remember that you need 3 cones to make a cylinder. So a cone is 1/3 of a cylinder. So the volume of a cone is 1/3 pi r squared height. Next, spheres and hemispheres. Simply remember that we need 2 cones to make a hemisphere. So if the volume of a cone is 1/3 pi r squared height, the volume of a hemisphere is 2/3 pi r squared height, but instead of height, we will be using radius. So it will be 2/3 pi r cubed. And of course, we need 2 hemispheres to make a sphere. So the volume of a sphere will be 2 times of the volume of the hemisphere. So it will be 4/3 pi r cubed. And here is a quick reference sheet of all the areas, surface area, volumes of different polygons. You can take a screenshot if you want to. Moving on to the steps in solving optimization problems. First is we have to read the problem until we're sure that we have completely understood and we have a basic grasp of what's happening, what's required in the problem. So I gave an example here. The product of 2 positive numbers is 16. Find the numbers if the sum of one number and the square of the other number is least. So a very helpful tip is to draw a diagram, but in this case, since it is a number problem, we can just write the equation given in the problem. Okay, let's first list all the given. Let x be the first number and let y be the second number, and let s be the sum of 2 numbers. So based from the problem, we understood that the product of 2 positive numbers is 16, so we write using the given variables here, x times y is equals to 16. And if we're going to find the sum of one number and the square of the other number, we will write it down as s, which stands for the sum, is equals to x, which is the first number, plus y, which is the second number raised to 2. In optimization problems, it is either we are minimizing or we are maximizing. In this case, we are minimizing the sum of the two numbers. The next step is to identify what is required and what needs to be optimized. So it is required that we know the x and the y, and they will be our independent variables because they are our unknown variables. And our dependent variable is the variable or the quantity that needs to be optimized or minimized or maximized. So Rs will be our dependent variable. The next step is to relate all quantities in the same equation. So we were given two equations, or rather we wrote down two equations. So the first equation was x times y is equals to 16, and the second equation was s is equals to x plus y squared. A very helpful tip is to express one variable in terms of the other. And in this case, we want to express our y in terms of x. So based from the first equation, we will find y in terms of x. So that would be y is equals to 16 over x. And now we will substitute our y in terms of x in the equation, resulting in s of x is equals to x plus 16 over x quantity square. So that will be our working equation. Now that we have our working equation, we can differentiate the dependent in terms of the independent. So we will differentiate s of x in terms of x. So let's write that down. So our working equation earlier was s of x is equals to x plus 16 over x quantity squared. Differentiating that would result to s of x over dx is equals to 1 minus 512 over x cubed, using the chain rule and the power rule. Next step would be to equate the first derivative to 0 and solve for the critical points. Multiply both sides by x cubed, and that would be 8. Now note that we can substitute x is equals to 8 in this function, in this equation, which will give us 16 over 8, and that will be equal to 2. And we can check this by multiplying 8 times 2, and that would give us 16. Another optimization problem includes maximizing the volume of a geometric figure. In this case, we are going to maximize the volume of the box. So the problem says, if 1,200 square centimeter of materials is available to make a box with a square base and an open top, find the largest possible volume of the box. So here you need to visualize the geometric figure. In this case, we are going to look for the maximum volume of an open top box. So a box with no top and a square base. So I drew here our given, which is a box, and we have a square base and the top is open. Let x be the side of the base and let y be the height of each side. So as we know from the previous video, the area of a square is x squared. So we will write it down as one of our formulas. The area of our base is x squared, and we cannot be certain that the sides will be square. So just to be safe, we will designate it with x and y, where y is the height of each side. So the area of each side will be xy, and since we have 4 sides in total, it will be 4xy. were given the surface area. The surface area is basically the sum of all areas. So in the problem, it says 1,200 centimeters square of materials. So we will be using a surface area of 1,200 square centimeters. And if we're going to write it down in an equation, it will be equal to x squared plus 4xy, where x squared is the area of our base and 4xy is the area of our sides. Now that we have it all written down, we will now solve for the volume of the box. So the volume of the box is equals to x squared times y, where x, y are independent variables because it is the unknown values, and our volume is our dependent variable because it is the quantity that we are going to be optimizing. So note that 1,200 is equal to x squared plus 4xy, since this is our equation for surface area. And a tip that I mentioned earlier is to express one variable in terms of the other. So in this case, we are going to express y in terms of x. So isolating y in one side will give us y is equal to 1,200 minus x squared all over 4x. And now we will be substituting that to our volume formula, which will give us v of x is equal to x squared multiplied to 1,200 minus x squared all over 4x. And we can further simplify this by dividing both terms by 4x. The next step would be solving for the first derivative. So let's differentiate v of x in terms of x. That would give us x squared multiplied to the derivative of the second term, which is going to be negative 300 all over x squared minus 1 over 4. And we're going to add it with the second term, which is 300 over x minus x over 4 multiplied to the derivative of the first term, which is 2x. And now we will be distributing x squared to each term. That would give us negative 300 minus x squared all over 4. And for the second term, we will have 2x multiplied to 300 over x will give us 600 minus x over 4 times 2x will give us x squared over 2. And combining like terms will give us 300 minus 3x squared over 4. And that is our first derivative for v of x. And if you may recall, the next step would be to equate the first derivative to 0 and solve for the critical points. So we will be equating 300 minus 3x squared over 4 to 0, and we're going to move 300 to the right hand side. That would give us negative 3x squared over 4 equal to negative 300, and multiplying both sides by 4 will give us 3x squared equal 1,200, and divide both sides by 3 will give us x squared is equals to 400. Let's solve for the square root of both sides, and that will give us x is equals to positive or negative 20. But of course, we can't have a negative measurement in the volume, so we will be considering negative 20 as our extraneous root, and we will be only considering positive 20. So if our x is 20, that means that our y will be equal to 10. And the maximum volume will be x squared times y, where x is equal to 20 and where y is equal to 10, and that would give us 4,000 cubic centimeters. So as for a quick summary, what we did to solve an optimization problem is we began by drawing a picture and we assigned variables. The next step is finding an equation that would relate all the variables needed. And if you may recall, we expressed one variable in terms of the other to describe the quantity that would be minimized or maximized. And lastly, we look for critical points by equating the first derivative to 0 and solving for the roots. And that's it for optimization video. If you have any questions, you may email chen.acads@gmail.com or you may reach us to our Facebook page, Chen.acads Hub. Thank you so much and have a great day ahead.